Hello everyone. So today let's solve the problem number 332, reconstruct itinerary, right? So what is itinerary here? This may look this one fancy actually. It's nothing but suppose if you have a source, suppose you stay in we stay in Bengaluru, right? So we plan a trip actually. Suppose we plan a trip, and accordingly with the trip actually we'll be planning certain this one. There should be a destination, right? So there should be some places to visit actually, and also the route. Via something we have to go, we have to travel, right? So that route and this one, what do we call the destination or the places that we plan, that planning we call it as itinerary in simple terms. Yeah, so we have to reconstruct the itinerary, right? So let's see what the question states here, right? So we are given flight tickets that is represented as fares, this one from and to, right? See here, we have been given flight tickets that is represented as fares. So this is nothing but from, and this is nothing but to actually. From and to. From certain place going to certain place, right? So this is fine. We must reconstruct the full itinerary that starts from JFK. That has to start from JFK itself. They have strictly mentioned that it has to start from JFK itself. So initially we have to consider this one from the JFK itself. They have strictly mentioned in the question. We must reconstruct the full itinerary that starts from JFK and uses all tickets exactly once and uses all the tickets exactly once. If multiple valid routes exist, see here, if multiple valid routes exist, then we have to return the one with the smallest lexicographical order. If multiple smallest routes exist, then we have to return the one with the smallest lexicographical order, right? Each ticket can only be used once. Each ticket, one ticket, whatever the ticket that we use actually, each ticket can be can only be used once, and all the tickets form a valid path. They have mentioned that all the tickets form the valid path, right? So this is it for the question. So first what we'll do, see here, this is from, this is to, this is from, this is to, this is fine. Again, the output we will start from JFK, we'll go to MUC, this one, then we will go to LHR, then from LHR to SFO, then to SJC. So this forms the valid path, and this path we have to this one, what do we call, return actually, and we have to start with JFK. So this is the input. Again, we have to start with JFK at any cost, and we have to visit all the nodes. We have to visit all the nodes, in the sense we have to visit all the places, right? In this case, they have given JFK, MUC, something in the form of this one, characters they have given, right? MUC, uh, this one, LHR, this one, weird characters. This is fine. Anyways, yep. Here JFK to MUC, MUC to this one, LHR, LHR to SFO, and SFO to SJC. This forms the path actually, right? So this one we have to return. The same goes with second one as well. Tickets we have been given JFK and SFO, JFK ATL, SFO ATL, ATL JFK, and this one. The output will start from JFK. JFK to we will be going to ATL, right? ATL. ATL again will come back to JFK, again will come back to JFK, and we'll go to this one, SFO. From SFO, we will be going to the this one, what do we call, ATL. From ATL, again, we will go to the SFO, right? Again, we'll go to the SFO. So see, another possible reconstruction is possible, but it is larger in lexicographical order. So in the question, they have strictly mentioned that if multiple valid paths exist, then we have to return the one with the smallest lexicographical order, right? So that's what. Yep. So this is fine, I believe. Now let's do one thing. Let's consider the same first example for the approach, and let's discuss the approach. Yeah. So first thing I want to tell you here is we will be going with a higher Holz's algorithm, right? Higher Holz's algorithm. So if you don't know higher Holz's algorithm here, one second. Yeah. If you don't know higher Holz's algorithm, you can just go through the this one graph based algorithms playlist, and you can just search for Eulerian path or circuit, Eulerian path or circuit algorithm. There you'll find the this one. We have written the algorithm to find the Eulerian path or circuit using the higher Holz's algorithm, right? So you can just watch the algorithm and you can come. So the implementation will be easy if you know the algorithm. Yeah. So this is basically we make use of the higher Holz's algorithm or the Eulerian path or circuit. So it's used to find the this one higher Holz's algorithm. It is used to find the Eulerian path of the circuit in a graph. We know that, right? So nothing but when I say Eulerian path of the circuit, that is nothing but the path that visits every edge exactly once, right? From one particular this one node, we will be this one we'll be finding a path that visits every edge exactly once. So that is the reason we make use of the higher Holz's algorithm, right? Again, higher Holz's algorithm, it is used to find the Eulerian path circuit. You have to know what Eulerian path circuit is, right? So again, I can't explain you the entire thing, but you can just go through the graph place, this one playlist there. You can just find the Eulerian path of the circuit, and you can just watch the algorithm. I have explained step by step, and then you can come back here, right? So I'll understand the whatever we are solving quickly. Higher Holz's algorithm is used to find an Eulerian path or circuit in a graph, a path that visits every edge exactly once, right? So we use it here basically for the for this particular problem because each flight ticket, nothing but the each flight ticket is we are discussing or we are considering that one in the form of edge, right? Each flight ticket or the edge must be used exactly once, forming a continuous valid itinerary, So just keep this in mind. Yeah, just keep this in mind. Next, what we will be doing here, let's move on with the further things here. Yeah, let's move on with the approach part. Let's move on with the approach part. So let's consider the same first example for the approach. So you can just implement the same thing for the second one as well. So whatever we discuss here, so you can just try to implement or articulate the same thing by considering example 2 as well. Yep. So first, what we'll do, we'll build a graph where each airport, this one points to the list of destinations, right? We have to consider initially, we have to start with JFK itself. They have strictly mentioned that one in the question. First, from JFK to MUC. See here, we have JFK to MUC, right? So first, we can consider in this way, JFK to MUC, right? So this is one thing, and then MUC to LHR. They have given here MUC to LHR, right? And they have strictly mentioned that we have to start with this one JFK itself, right? JFK to MUC, MUC to LHR. Then we have SFO to SJC, right? Or then we have actually LHR to SFO, right? LHR to SFO because we have to go with a lexicographically smaller one, right? LHR to SFO. Then we can consider this one, the final one, SFO to SJC, right? SFO to SJC, right? So this is the first step, right? So we have successfully built the graph where each airport points to the list of destinations, right? So this is fine. Next, what we'll do, we'll sort each destination list lexicographically for the smallest order, right? Here in this case, it is already sorted. We have already sorted, right? JFK to MUC, IJKLM, M, IJKLM, this one, this one, what do we call? MUC to LHR, right? Yeah, MUC we have already considered. So MUC to LHR, LHR to this one, SFO, and SFO to SJC, right? So this is already sorted. We'll be sorting each destination list lexicographically for the smallest order. Here, in this case, it's already sorted. So then what we'll do, we'll perform DFS starting from the JFK. We'll perform DFS starting from the JFK. If you know the higher this one House's algorithm, we should be able to implement this one in a this one fast actually. Let's perform the DFS starting from the JFK. So first what we'll do, we'll go to the smallest available next destination. The smallest available next destination is from JFK. Rather than I drawing the graph, I'll just consider this diagram itself. From JFK, we'll be moving to the MUC, right? So this is directed from this one JFK, we are going to the MUC. From MUC, we are going to, after sorting, we are going to the LHR, right? The same thing they have shown here. From MUC, it's LHR, right? So from LHR, we are moving to the SFO. From LHR, this one, we are moving to the SFO. This is fine. Next one, from SFO, we are moving to SJC. From SFO, we are moving to SJC, right? So this one. So this is it. So this is it. When we can't go further, we will be adding the airport to the result, nothing but the post order, right? So we will reverse the result at the end. that gives the correct itinerary, right? So this will be basically JFK MUC, this one LHR. This one will be considered from MUC to LHR, right? So we are considering. So this one will be going with the MUC to LHR. Then will not be considering LHR to SFO. This one to this one, and finally SFO to SJC. Yep. So it will be the same diagram: JFK to MUC, MUC to LHR, LHR to SFO, and SFO to SJC. So this is the output that we get actually. Yep. So I hope this part is completely clear, right? So now, as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part. So what will be the time complexity here? The time complexity would lead to Pico of E log E. The time complexity would lead to Pico of E log E, right? So why it is E log E? Each ticket, so we are going with each ticket insertion and poll from the minimum heap that costs log E. That costs log E actually. Overall time complexity would lead to Pico of E log E, right? So this is the overall time complexity. So what would be the space complexity here? The space complexity would lead to Pico of V plus E, right? So it's V plus E because we have to store the graph and we have to go with the recursions. We will be going with the recursion stack as well. So overall space complexity would lead to big of V plus E. The time complexity and the space complexity for the code that we'll be writing in the future would be big of E log E and big of V plus E respectively. Now, as we are completely familiar with the approach as well as the complexities part, we are good to write the code. Let's start writing the code actually. Yep. So the first part here would be, first let's build the adjacency list graph as discussed in the approach. So I'll just go with your map string. I'll just go with a priority queue. So this is fine. Of string, this is fine. Let me go with graph and let me assign this one to new hash map. This is fine. So the next step would be, let's go with a for loop here. So this one will be list of string. So this is fine. List of string. Let me consider individual t of tickets actually. Yep. So within this for loop, let's do one thing. Each departure points to the destination that is stored in the minimum heap, or this one priority queue basically, right? So I'll just go with your graph dot, let me go with compute if absent, that the hash map provides actually one of the operations, right? I'll just go with compute if absent. So I'll just go with t dot get here of 0. Yep, t dot get of 0. Okay, just go with new priority queue, right? So I haven't written priority queue. I have written right already. Or the priority queue without initializing this. Yeah, so this is fine. Priority queue, I'll just go with offer as discussed. Offer, we have to get this one, the value. Right? So I'll just go with t dot get of 1. Yep, let me give semicolon and let's move on actually with the further things. Yeah, this is fine. So the next step would be the second step. Let's go with the result list to store the final itinerary, right? So I'll just go with the linked list here. Linked list of string, this one, itinerary. So this one, I'll just set this one to. So let me copy this one instead of typing. Yeah, let me paste this one over here. Yep. So the next part, the third part, if you remember the this one approach, so we have to go with the DFS function, nothing but the higher Holz's algorithm, right? So for that, before making use of it within the main function, this one main method or the function, this one find itinerary. So let's go with the helper method DFS, right? So we have to perform DFS first, then we can make use of it on this one main method of the function. Void DFS. I'll just go with here. I need some of the parameters. One thing is I need airport, right? Also, I need this one. What do we call? Uh, Graph actually, right? So this one I can just write it here. Map string priority queue. So this is fine. Of string, queue of string. So this one I'll just go with a graph. Next, let me go with a linked list actually of string of string. So this is fine. Linked list of string. Let me go with a result actually. Let me go with a result. So within this helper method, DFS, the first thing that we will be doing here is while there are remaining destinations from the current airport, so in that case, we have to always choose the lexicographically smallest destination, right? So let's write the while condition first. So this one is graph dot, I'll just go with the, sorry, uh, contains this one. Let me go with the contains key here. So we have to check while there are remaining destinations from the current airport, right? So I'll just pass the airport here and I'll just go with not of graph dot get of this one airport actually dot is empty dot is empty. So here within the while loop, so let's always choose the, or we have to always choose the lexicographically smallest destination. So I'll just go with variable next here, which is of the type string. Let me give graph dot get of airport dot pole. Yep, airport dot. Finally, let's recurse here. I'll just go with DFS of next, comma, uh, graph, and I have to pass the result as well. Yep. So finally, what we have to do, we have to add the airport after visiting all the destinations in the, which is nothing but the post order actually. We have already discussed this one. So I'll just go with add first operation and let me pass here airport. So this is fine. The final step here, we have went with the linked list here, so this is fine. So now we'll be making use of the DFS, or we'll be calling the DFS function within the main method, right? Find itinerary method. So I'll just go with DFS, and in the question they have strictly mentioned that we have to start with JFK at any cost, right? Let me go with JFK here, graph, as well as let me pass the itinerary. So I'll just go with where is this itinerary? I used somewhere, man. What? 1 second. Yeah, here itself, right? Let me go with itinerary here. The next step would be the final step. All we have to do is we have to return the itinerary. Means it's already reversed by construction, right? All we have to do is return the itinerary, right? So this is it for the code, right? Just give me a second here. Let me format the code once and let me hit the run button. This has to work. Let's see. This is pure this one. What do we call? This is purely based on Hierholz's algorithm actually. Yeah, you have to know the Eulerian path or circuit. So to find the Eulerian path or circuit, we'll be making use of the Hierholz's algorithm. So again, why we are making use of the Hierholz's algorithm here? Again, Hierholz's algorithm mainly it is used to find the Eulerian path or circuit in the graph. If you don't know it, just go to the graph algorithms and graph-based algorithms, and you can just watch the video there, or you can just learn the algorithm, or you can just see what we have discussed there and you can just come back, right? Hierholz's algorithm is used to find the Eulerian path or circuit in the graph, a path that visits every edge exactly once. Here in the question, they have strictly mentioned we have to this one visit every edge exactly once, right? So and also we if there are multiple paths, in that case we have to return the one with the smallest lexicographical order. So that's what they have asked in the question. So we use it here because each flight ticket, nothing but the edge that we are considering, it must be used exactly once, right? Forming a continuous valid itinerary, right? So that is the reason we are going with a higher Holz's algorithm. So it is the most this one. The algorithm basically fits, right? Uh, for this particular question, right? So it's better to go with this particular algorithm, right? So this is fine, I believe. So let me hit the submit button. The sample test cases have got passed here. I hope this works for all the test cases. Yeah, you can clearly see here all the test cases are getting passed. So whatever the code that we have written works absolutely correct for all the test cases, right? I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.